real-time location detection of laying hens using a wireless body-mounted area sensor network. The work presented in this video was done in the NeEWS laboratory in the Animal Behavior and Welfare Laboratory at Michigan State University. This system has many production and animal welfare applications. The objectives of our work are to develop a hen location and proximity detection mechanism that can provide real-time, automatic location detection of hens in a cage-free system which can monitor multiple birds simultaneously with minimum detection error. This picture shows our implementation of the wearable sensor network. As the bird approaches a resource, the software can identify which resource the bird is closest to and can indicate where she is at all times. The stationary sensors can estimate the proximity of the hen to each sensor by measuring the radio signal strength between the static sensor and the sensor attached to the hen. Our system is designed to detect a wide array of species-specific and resource-oriented behaviors. For this application, we placed one sensor in 3 points throughout the room. One on the feeder, one above the nest box, and one above the perch. These stationary sensors are composed of Mica 2 mote radio nodes that operate at 900 MHz channels and a sensor card NeEWS.wmv, both of which come from Crossbow technology. Information from these sensors will be sent to a wireless base station located outside of the room. This data is processed by the server to determine the correct location of the hen. Continuous video recordings and infrared lighting in the room are used to validate the output from the sensor software. The sensor is mounted on the back of the hen in a lightweight plastic casing using a figure-8 nylon harness. Both the sensor case and harness have been colored to blend in with the hen's feathers to avoid attracting attention to the package. The Mica 2-dot mote radio nodes with sensor card MTS510 worn by the hens weigh approximately 10 grams and are placed inside the plastic casing after it has been attached, and the uniquely labeled plastic cap is screwed on. In order to avoid the medium access collision inherent to TinyOS working stack, we have implemented a higher layer polling base time division multiple access strategy, which is managed by the base station node. The base station node polls the mobile nodes worn by the bird in a round-robin fashion. A mobile node sends a beacon packet only when it is polled by the base station for giving access to the channel. In addition to 5 mobile nodes, there are 3 stationary nodes. For the 8 nodes in the network, a polling time frame of 1.5 seconds is used. The 8 nodes form a mobile network for which a mobile routing protocol, namely ad hoc on-demand distance vector, was used for data collection. This is an example of the hen making a transition from the feeder to the nest box. Displayed is the data which is processed by the server as the bird makes the shift from one station to the next. The radio signal strength data can identify the proximity of the hen from the resource. A high radio signal strength indicates close proximity to a resource, and a low signal strength indicates that the hen is farther away. Therefore, as the bird transitions among the different resources in the room, the software can identify where she is moving based upon the relative strength of the radio signal strength from each static sensor. These graphs illustrate the percent match between the video observation and the output from the sensor system. As illustrated, the feeder produced an 82% match. The nest box produced an 84.6% match. And the perch produced an 89% match between the sensor output and the video observation. This graph shows the percent match between the video recordings and the sensor software over a 20-minute time interval. This illustrates the percentage of time spent at each of the 3 locations over a 50-second time interval. Please feel free to contact the authors for any questions or comments. Thank you.